Hello, Daisuke.
Hello.
Hello. Hello. Hi. Hi, Daisuke.
Hi.
Hello, hi Daisuke, can you hear me?
Yes.
Maybe you could share the screen.
Yes. So can you see my slide?
Yes, I can.
Okay. Okay.
Make it full screen, please. Okay, great. So we can see your slides.
Kadohさん聞こえます？
聞こえます。
レクチャーの続きをしようとしてます？それか、リサーチ
僕
投稿しようと。
単にとりあえず、何も用意したものがないんで、スキップした部分を話そうかとしてた。
あ、わかりました。
質問でもいいです。何でもいいです。とりあえず用意したものは何もないです。はい。さっき気づいたんで、このセッションがあるの。
あ、で、加藤さん、その方針で全然問題ないみたいです。
はい。
So welcome to the last session of the last day of the program. So our next speaker is Daisuke Kadoh. So Daisuke is going to continue with the tensor renormalization method. Daisuke, please go ahead.
Okay, thank you. And I don't have anything prepared for this session because I found out today that there is this session in a reminder email. But I skipped talking about the secondary normalization group method in my lecture. So I'll talk about SRG method. Oh, sorry. Okay. Okay. And the second renormalization group method is an improved TRG method. Sorry. And the SRG method was originally proposed on honeycomb lattice tensor network. And TRG was can be also defined on honeycomb lattice. And on the honeycomb lattice, the tensor is rank 3 tensors. So the two rank 3, this M is made of two rank 3 tensors. And in the TRG on honeycomb lattice, this M is decomposed into two rank 3 tensors. And the TRG for honeycomb lattice tensor network is formulated by repeating this decomposition again and again. But this decomposition is locally carried out. So the information of environment tensor is just ignored in this decomposition. This ME is the environment tensor, meaning that M is removed from the whole of the network. So the ME environment tensor ME contains many tensors and many tensor tensor contractions. So actually, it's difficult to obtain ME exactly. So instead of ME can be approximately evaluated by tensor renormalization. And this figure shows a tensor renormalization for environment tensor ME. And repeating this tensor renormalization for environment tensor, this ME is approximately obtained. The once ME is obtained, this ME is obtained. So the influence of the environment tensor is included into the decomposition of M. And so this decomposition, the decomposition of rank hole tensor is locally carried out, but in this sense, the global information can be included in this local decomposition. So the accuracy of numerical results is improved by second renormalization group method. And for square lattice tensor network, the environment tensor TE is rank hole tensor. T is rank hole tensor, and T is removed from the whole tensor network. Then this the rest of tensor network, removing a single T, is environment tensor for the square lattice tensor network. And T also contains the many rank hole tensors and many tensor contractions. But it's possible to evaluate TE approximately using tensor renormalization. And this figure shows a tensor renormalization of environment tensor TE. And in this figure, two tensors in environment tensor are renormalized into a single tensor. So E of n denotes the environment tensor at nth renormalization step. And so these T's are tensors at nth renormalization step, Tn. And by using projectors Un, these Tn, two Tn's is renormalized into Tn plus 1. And so these tensors are Tn plus 1, but this part is not renormalized. So this part is made of Tn and Un. And so renormalized environment tensor is a product of En plus 1 and Un and Tn. So we found this recurrence relation from this figure. So En is obtained by solving this recurrence relation. And once En is obtained, the isometry can be updated from using the environment tensors. So firstly, we define this xn from this, and so diagrammatically xn is expressed like this, and xn is made of environment tensor Tn and two Tn's and Un. So one Un is removed from the whole tensor network. So the partition function itself is given by Un and Xn. And so Xn is given, then we perform the SVD for this Xn. So two unitary matrices U and V are obtained from the SVD of X. So this project is updated from these two unitary matrices, and by using this updated unitary matrix, projector, G is approximately given by singular values of X. So this U includes this U includes the information from the environment tensor. Okay, so and this summarizes the renormalization step of higher order SRG. The firstly, the Tn and Un are generated by the normal higher order TRG, and Tn and Un are the initial set of the tensor and isometries at the nth renormalization steps. Then we use forward and backward algorithms that repeats this one and these two steps. The first step, the environment tensor can computed by solving the recurrence relation, and the environment tensor is obtained. Then two procedures are repeated. The UN is updated by using this procedure, and then U is updated. The renormalized tensor T is updated by using this projector. So repeating these two procedures, the information of the influence of environment tensor is incorporated into the Tn. Okay, so by using these two steps, the accuracy is accuracy of results is improved. And this figure shows the numerical results of SRG schemes into dimensionalizing model. And blue and red are the results of SRG and HOSRG, and the SRG schemes drastically improve the accuracy of TRG and HOTRG. So, okay, so and I proposed that the SRG scheme in the triad SRG in 2 dimensions, and in 2 dimensions, triad representation of rank 4 tensor is a product of two rank 3 tensors. So two-dimensional tried tensor network is just a honeycomb tensor network. So 2D tried TRG is the same as that the HOTRG like renormalization for honeycomb lattice tensor network. But without any improvements, the isometry U and nu triads are constructed by ignoring the influence of environmental tensors. So we prepare the environmental tensors by using rank 3 tensors. And the HOSRG like recurrence relation was given by the triad and rank 3 environmental tensors. Then the cost of the triad SRG is proportional to d to the fifth, which is smaller than that of HOSRG. And this figure shows the numerical results of free energy. And red points are the results of HOTRG, and blue ones are HOSRG results, and greens are triad TRG results, and yellow are triad SRG result. As can be seen in this figure, for a fixed D, the HOSRG shows the best performance. Okay, so however, this figure shows D-cut dependence on this figure shows the time, real computational time, and the x-axis is D-cut. So from this figure, the HOTRG and HOSRG scales with d to the 7th, and the computational time of triad SRG and triad TRG scales with d to the 5th. These dependencies theoretically reproduces the theoretical expectations. And this figure shows the relative error of free energy against computational time. For fixed computational time, the triad SRG shows the best performance. So the SRG method effectively works with the triad TRG method. Okay, so so if you have a question, please ask me a question. I want. Okay. So.
Does anybody have any questions? Okay, no questions at the moment. Daisuke, please go ahead. There are no questions from this side.
Okay. So. Yeah, but this is I talked everything. I talked everything that I wanted to talk. So, if you have any questions, please ask me.
Okay, great. So let's all thank Daisuke for the lectures and talk. So any questions, any general questions from any of the lectures? Yeah, Rich, please.
Are you posting your slides? Are you posting your slides on the Slack channel?
Okay.
That's my question.
Question? No, no, but it's possible to post it.
Good.
Okay. So yeah, so let's
Hello.
thank Daisuke Kadoh. Oh yeah, there is a question. Okay, yeah, Omega, please.
So yeah, I'll ask one thing. In the last slide, you mentioned something about random sampling. So as far as I know, the tensor network method basically is a deterministic method. So adding random sampling is like you are moving towards the probabilistic approach of it. So if you could comment on that.
Which slide?
The very last one, 114.
Here? Sorry, here?
114, yeah. About the 4D gauge theory, random sampling. So I was just a bit confused that as far as I know tensor networks, I think it is a deterministic approach. So adding random sampling means basically you are adding the probability to it. So if you could comment something on this one. Although you did mention that there are further improvements that needs to be done, but still.
Random sampling approach, I think we well approximate the hard measure at least in 2 dimensions and in 3 dimensions. So I think it's also works in 4 dimensions. So, but of course, it's very effective for strong coupling region. So in weak coupling region, some improvement of random sampling will be important. But basically, the random sampling method with some improvement will be useful to study 4D gauge theory using the TRG method.
Okay. Thank you.
Okay, so let's all thank Daisuke once more.
Thank you.
Hello, Andy, are you there?
Yeah, I'm here.
Okay, so maybe you could start sharing your slides.
Yes, I can do that. Is that?
Yeah, it's visible. Could you please make it full screen?
Yeah.
Yes.
Or maybe just a second.
Okay, great. So are you ready?
Is this okay?
Yeah, it is okay. So our next speaker is Andy Sturgeon from King's College London, and he's going to talk about CFTs with UM cross UN symmetry in 3D and the chiral phase transition of QCD. Andy, go ahead.
Thank you very much, and I would like to thank the organizers for the conference and for the invitation to speak here. So I will be talking about CFTs with conformal field theories with UM times UN symmetry. And I will present results of some conformal bootstrap analysis I have been working on for a little while now with Stefanos Kouzvos. This is going to be a paper on this, hopefully this month. So let's start with, you heard something about the bootstrap already, but perhaps we should start with a little bit of the logic behind it. And the logic is different compared to renormalization group methods that you may be more familiar with, which rely on thinking about the renormalization group flows and their endpoints. So we always imagine that we are in some UV conformal field theory, maybe often a free theory, that we then deform with a relevant operator, which results in a normalization group flow, and then it terminates in the other endpoint in the infrared into some other conformal field theory that perhaps is strongly coupled or non-trivial more generally that we want to understand the properties of. That flow is governed by the beta function, and zeros of that beta function are the fixed points of the renormalization group. Now, the conformal bootstrap takes a completely different approach. It wants to completely get rid of this thinking and focus completely on the physics at the fixed points only. There will be no mention of how we got to the fixed points, what relevant operator would be formed by some UV theory to get to this IR theory. None of that information can be captured by the bootstrap. But regarding the conformal field theory that we are assuming we are probing, we will be able to understand a lot of aspects of it, including its spectrum of operators, scaling dimensions, OPE coefficients. That will give us basically a very good picture of the conformal field theory data that we're interested in and that are of relevance to experiments as well as theoretical, for theoretical questions. The way the conformal bootstrap does this is by considering constraints on 4-point functions of operators in the conformal field theory. Now, when we have conformal symmetry, 2- and 3-point functions of operators are fixed up to constants. There is no, the kinematics is completely fixed. The things that, the quantities that appear are the OPE coefficients or Wilson coefficients and the scaling dimensions. But the X dependence, if you want, of the 2- and 3-point function is completely fixed. In the 4-point function, this is not true because if you have 4 points in space, you can construct 2 separate conformal invariants. So the 4-point function will have some overall fixed X dependence, but then an arbitrary function of those conformal invariants can also appear. And looking at the 4-point function in the OPE decomposition way, where you bring operators together, you imagine they exchange an operator, and then that operator is also exchanged by the other 2. You can write a schematic representation of the 4-point function as you see here. And there are 2 different, well, there's more than 2, but it turns out that 2 of them give non-trivial, that one of them gives non-trivial constraints here. These ways to bring the operators together give rise to the crossing symmetry equation. Here you see that on the left-hand side, I bring together O1 and O2, and on the right-hand side, I bring together O1 and O4. And since it's the same 4-point function that we are discussing, it better be that these 2 different decompositions of the same 4-point function have to be the same. Now, if on top of this, you assume unitarity, which basically says in this context that operator dimensions lie above a certain unitarity bound, and the OPE coefficients denoted by C here, for example, C120 on the left-hand side, are real. So crossing symmetry plus unitarity turns out to lead to highly non-trivial constraints, as was realized a few years ago, maybe 12 or so years ago, numerically, because the resulting equations are very complicated and not easy to deal with analytically. However, numerically, we saw that they give rise to highly non-trivial constraints on the spectrum of theories. So the way we solve these bootstrap problems, and I should perhaps mention here that we call this the bootstrap because you see we're not solving any dynamics. We're not evolving any theory and trying to follow that evolution dynamically. What we're doing is we're using just constraints that the theory has to satisfy, and those are so restrictive that they allow us to uniquely determine, in some cases, theories that can satisfy them. And so it's this logic of getting something out of nothing in some sense. So more recently, this has been developed numerically because it was realized that we can map it into a semi-definite programming problem, and there are many algorithms and highly developed algorithms to solve such problems because they appear all over the place in science, also in industry. And the primary reason for the excitement behind the conformal bootstrap is, of course, that the results one gets are non-perturbative. There are no approximations involved, and therefore it is one of the few methods, along with, of course, Monte Carlo, that we have to probe the non-perturbative regime of conformal field theories. Now, the most striking results of the method so far have been found for three-dimensional conformal field theories, and those are very important due to their applications to classical critical phenomena. In particular, the Ising model has been analyzed to really great detail, as have the ON models. In my work, I have also analyzed other universality classes like the cubic universality class you may have heard of, and others. There has also been a lot of lattice work in some of these. The bootstrap has also been applied to superconformal field theories, defect CFTs. This logic of the bootstrap has been adapted to treat all these types of problems. And today, I want to discuss the application of the conformal bootstrap to the chiral phase transition of QCD. Perhaps I hope that this will be of interest to the audience, given the interest, of course, in QCD and its properties. So let me pause and ask for any questions up to this point.
I don't see any questions.
Okay, very
Please,
good.
go ahead.
Thank you. So let me just summarize a few known things to everyone there, I'm sure, about the chiral symmetry of QCD. So if we start with the Lagrangian of QCD, and we will imagine we have NF general, NF fundamental quarks. At the classical level, we have UNF left times UNF right global symmetry, which we will write as SUNF left times SUNF right times some vector and some axial part. And the vector part, the U1B part, is not chiral, so we will forget about it. And there is also a very concrete understanding that at zero temperature, the U1 axial anomaly symmetry is anomalous and therefore broken. And so we end up in the quantum theory with SUNF left times SUNF right global chiral symmetry. Now, in the vacuum of QCD, the quark condensate, which is Q bar left, Q right, breaks the chiral symmetry, and the pattern of the symmetry breaking is such that SUNF left times SUNF right goes to the diagonal SUNF. And this is the situation. This breaking happens at some non-zero temperature, where for the case, for example, of two massless quarks, as we will review later, it's about 160 MeV. Now, there are two quarks that are much lighter than these, up and down, and a third one that's a bit lighter, the strange quark. And therefore, when we study the nature of the order of the chiral phase transition of QCD, we are considering either two or three quarks as massless, and the rest are considered infinitely heavy, compared basically to the critical temperature that we have. So in this context, we want to understand what the order of the chiral phase transition is. It's a phase transition that happens at some non-zero temperature, and it is not clear what its order is. Is it first order or is it second order? And this was a question first posed by Pisarski and Wilczek in 1984. Now, The breaking of the axial symmetry of the axial U1 in QCD was, of course, understood by 't Hooft to be due to instanton effects. This is very well understood at zero temperature. But in various papers and old work by Pisarski and other co-authors and authors, the non-zero fate of the U1 axial symmetry has been the subject of sort of controversy, as far as I understand. I'm not an expert in this, and there are people in the audience that know much more about this than I do. But it is my understanding that although at zero temperature, of course, the effects of the breaking are there and the axial symmetry is broken, at non-zero temperature, there is a suppression of the instantons. It's an exponential suppression where rho here is the size of the instanton. And this exponential suppression that may suppress the effects of the axial anomaly breaking and therefore result to the axial symmetry being effectively restored at high temperature. This has been studied theoretically. There have also been lattice simulations that have tried to see if the breaking of chiral symmetry of the axial part of the chiral symmetry persists at non-zero temperature. And the conclusion to me, by looking at the literature, seems to be that at high enough temperature, indeed, and close to the critical temperature, indeed, the axial symmetry is restored. So this is the question is if SUNF left times SUNF right times UN axial at non-zero temperature should be reduced to SUNF left times SUNF right. In the high temperature phase, what is the global symmetry? Because we need to know the global symmetry at the high temperature phase in order to find potential universality classes of theories that a potential second order phase transition for QCD might actually be part of. And for example, if you have two massless flavors, you either have O4, which is SU2 times SU2, or you have O4 times O2. And of course, we all know the O4 universality class. So if the axial symmetry is not effectively restored at non-zero temperature, there is a belief that the symmetry, the chiral symmetry breaking is of second order and of the O4 universality class. But if it is effectively restored, then we have O4 times O2, and it is of interest to look for universality classes with that global symmetry to see if in that case, the chiral symmetry breaking of QCD may be second order. So this brings us to the study of the so-called UM times UN models. Of course, we're looking for a theory in 3 dimensions. We're looking for a conformal field theory in 3 dimensions. And in order to model this, we will consider the field phi, which you can think of as the quark bilinear that I mentioned before. This is the order parameter of the symmetry breaking. It has 2 indices, A and R here. A runs from 1 through M for the UM, and R runs from 1 through N for the UN, and it's a bifundamental under UM times UN. If you were to write down a Landau-Ginzburg theory for this matrix, you would write this Lagrangian over here. You have 2, you would write, of course, your free theory. You can add your mass term, and you would have 2 couplings. One is the square of the trace of phi dagger phi, and the other one is the trace of the square of phi dagger phi. And when you compute the beta functions for these couplings lambda and g in 4 minus epsilon dimensions, what you find is that there are up to 4 fixed points. The Gaussian fixed point is always there, where lambda and g are 0. You have a fixed point with enhanced symmetry. If we set lambda to 0 and keep g non-zero, then the symmetry enhances to O 2 times m times n. And then there are 2 fixed points where lambda and g are both non-zero, that typically are denoted by this U plus minus in the literature. Now, these fixed points don't exist for all values of m and n. If you take some m and sufficiently high n, then you are in this situation 1 here, where you have the fixed point U plus being the renormalization group stable fixed point. You have the Heisenberg fixed point, or not Heisenberg, but I mean the O2mn fixed point also there when g is 0. And you have the U minus fixed point and the Gaussian fixed point, and U plus fixed point is stable. But as you change n at that for fixed m, the two fixed points U plus and U minus move around in this plane and they actually collide. When they collide, we lose them as unitary fixed points, and we transition into situation 2, where we only have Gaussian and Heisenberg, and none of the two are stable. As you keep changing n, the two fixed points actually reappear in the real plane, but now they appear with the opposite coupling G, the opposite value, the opposite sign for the coupling G. And U plus remains stable. And as you keep changing things, so that's situation 3, and as you keep changing things, then the coupling of U plus, the G coupling of U plus changes sign again, so that it's the orthogonal fixed point, the one denoted by H in situation 4, that becomes stable. Now, the values where these transitions happen can be computed in the epsilon expansion, and there have been many papers recently, over the years, and also recently doing this. One thing to point out is that for the correct symmetry break-in, where we want SUNF times SUNF to go to the diagonal SUNF, we need this coupling G to be positive in order for the potential to break the symmetry in that specified way. And of course, we also need a fixed point to be RG stable, because we want our RG flow to reach that point. We do not want a relevant operator beyond the mass operator at that fixed point. So the question is then, if we go back one slide, what are the values of M and N for UM times UN fixed points for which we are in situation 1, where we have G positive and the U plus fixed point being stable? This is what we want to look for. And in the epsilon expansion, what's typically computed is the quantity n plus of m in 4 minus epsilon. So we fix m and we compute the value of n for which we transition from situation 1 to situation 2. And we want to be at an n higher than the critical n we computed, so that we are in situation 1. There have been many papers computing this over the years, as I said, and this was recently done up to 6 loops, which is order epsilon to the 5 for this quantity. And of course, we need to take the epsilon to 1 limit, but and this is something not well defined, but let me show you how these expressions look. So if you fix m to 2 and you compute this n plus in 4 minus epsilon, you get this series over here. It's not going to be a convergent series or anything. We know it's asymptotic, but there have been various resummation techniques employed, and for m equal 2, the result is that the critical value of n is about 4.4. So you need to have, in a UM times UN theory with m equal 2, you need to have an n of 5 or higher in order to be in situation 1 and have a stable fixed point that can host a phase transition that is second order. This is clearly not the case for QCD with 2 massless flavors, because that would then mean that the 2,2, the theory with m equal 2 and n equal 2, which is the case of QCD with 2 massless flavor, falls below this value. N is 2 and therefore below this value of 4, and the theory does not have a fixed point. Therefore, the phase transition in that case would have to be first order. You can repeat the same exercise for m equal 3, and then again, you see that the n that you get is larger than 3, and therefore, again, in this case, of 3 massless flavors in QCD, you do not have the possibility of a second order phase transition. Now, this relies on resummations after the epsilon expansion. There has been some work where people resum the beta functions themselves and then look for fixed points of the resummed beta functions. And those are not guaranteed to be the same as the ones that you find in the unresummed beta functions. There have been some hints doing that there is a distinct universality class than the one discussed in the standard epsilon expansion, but the fact that these are uncontrolled approximations perhaps is unsatisfactory, and we would like to have a better way. And the better way that we are going to pursue here is the conformal bootstrap way. And This relies looking on a 4-point function. So here we will look at the 4-point function of the order parameter operator. We have phi, phi dagger, phi, phi dagger, and we will analyze this in all possible channels that it has. And first, we need to understand some of the group theory. If we had phi in the fundamental of UN, just one UN, then we know that if we bring phi and phi dagger together, what it exchanges is singlets and adjoints. And if we bring phi and phi together, it just exchanges symmetrics and antisymmetrics. These are representations of every spin, but under the global symmetry, they fall into these irreducible representations. Since we have UM times UN, and products of irreducible representations are irreducible, what we need to consider are products of these representations of UN. So the group theory here is actually not hard at all. It is easy because we know so well the group theory of UN. And here are some results. Let me show you some bootstrap bounds. So what we do with the bootstrap is we make an assumption on, say, the value of this operator phi that I was discussing here. We're in 3 dimensions, and therefore the lowest dimension that operator phi can have is 1/2. And then we are asking for what is the highest possible dimension of one of these exchanged operators. So we consider the OPE of phi with phi. We look at all the different irreducible representations on the other side, and we choose, for example, the spin 0 operator in the representation RS that I plot here, where RS means that I take the adjoint from the UM and the singlet of the UN. There's going to be such an irreducible representation on the right-hand side, and I want to find the maximum dimension for the operator of spin 0, the leading operator of spin 0 in that representation, for a given value of delta phi. And these are the kinds of plots you get. And you see very sharp kinks for large N, for example, the 220 theory here. And you can perform analytic computations at large N. We also did this it hadn't been done before, but we did it in this paper that will be coming out. And the dot that you see, the circle and the square that you see there are exactly the the U plus and U minus fixed point. The square is the U minus fixed point. The U plus fixed point is the circle. And at large N, you see just how well the kink in the bootstrap bound coincides with the position of the fixed points as derived from the large N results. When we look at N equal 10, it's still very good. Of course, as we decrease N, this becomes worse. And you see that the kink becomes milder and eventually disappears once you get to the to low N. This behavior of the kink, we believe, is basically the result of the fixed point moving into the non-unitary regime as we decrease the value of N. But it is very important that both universality classes are allowed here. You see that one saturates the bound, the other one is in the allowed region. Everything below these curves is allowed in the corresponding theories, everything above them is excluded. And this is a fully non-perturbative result. You can also do something else. You can take the singlet from UM, U2 in this case, and the adjoint from UN and get a bound on the corresponding leading spin 0 operator. And these bounds don't have spectacular kinks, but I'm just showing them to you to show you that indeed, again, they seem to be saturated at large N by, in this case, the other fixed point, the U minus fixed point. So here, it was the circle, the U plus fixed point, that was saturating the bounds. And here it is the U minus fixed point, which is the square that's saturating the bounds. So it's a good check, of course, on our computations at large N that we have set up the problem correctly, that we are doing the numerics correctly, that we are not excluding known theories, and this lends validity to our computations. Okay, so let's focus now on the U2 times U2 theory. The U2 times U2 theory, you can get bounds on all sorts of different operators. And these are all bounds on spin 0, leading spin 0 operators in the different irreducible representations of the global symmetry. You can think of them as quadratic operators. You take one phi and another phi, they have indices, and you bring these together in different ways to have the different irreducible representations, but they are all quadratic in phi. and no derivatives. They are spin zero, leading operators of spin zero. So you get bounds for all of them. And what I have denoted by the blue dot here is the O8 model, which is, of course, in the allowed region of all these curves. And while there are no kinks here, you see a kink in the AA bound. So here I have a plot just for that. So you take the antisymmetric from each of the U2s.
And do you have 5 minutes?
Yes, thank you. And you get this kink that was first noticed by Nagayama and Otsuki, and it was derived by some previous work that I did in 2020, which is indicating that there might be some CFT responsible for that kink in U2 times U2 theories. You can do the same thing for U3 times U3 theories. Again, there is the O18 model now, given by the blue dot. You get bounds again for all the operators. You don't see any kinks here. So you might believe that, oh, well, there is no CFT then. And so the three flavor massless QCD with effectively restored axial U1 will not be second order. But if you look at the larger region of parameter space, for example, in the RS operator, spin zero operator, you see a very well-defined kink for a larger value of delta phi. And you can then also study this kink and how it behaves as you change n, fixing m equal to 3. And you see it here in the bottom curve, that kink, and you see how as we increase n, it sort of disappears, and the kink that appears is the large n kink of the epsilon expansion that we described before. Now, these kinks are not, specifically the kink in the U3,3 curve here around delta phi equals 0.62 or so. The fact that it exists does not mean that we have a CFT that describes it, but it provides evidence that there might be a CFT with this symmetry that the second order, that the phase transition of QCD might have available in order for it to be second order. So let me summarize that the conformal bootstrap numerically is a widely applicable and robust method for the study of conformal field theories. The bounds that are produced are rigorous and non-perturbative, and kinks that appear in them correspond in many cases to known theories, and it is natural to assume that generally kinks correspond to CFTs that, even though may not be known, may be just as important as the ones that we know from the epsilon expansion and large n. For the case of massless QCD, for both with 2 and 3 massless flavors, I showed you evidence that there may be a universality class available for it to be second order in the case of effectively restored axial U1 at high temperature. Right. Thank you very much for the opportunity.
Thanks, Andy. Questions? Yes.
Can anybody explain to me why a kink should appear where a theory appears? Is there a physical reason?
No. There is a lot of evidence.
I know there's a lot of examples, but is there some
there is
argument that supports it in qualitative
There is no
way?
such argument. Sorry, go ahead.
No argument at all. I mean, I don't know.
Not that I know of. There is no argument why, for example, in this case, the U2 times U20 kink is so sharp and falls exactly at the position of the analytical computation that you can do. There is no argument.
But I mean, why would it be a kink? Maybe it should go the other direction. I'm trying to understand what kinks mean. No idea. Okay.
Mm-hmm.
Okay. More questions? Denju?
Thanks. I'm wondering, has anyone tried the fixed dimension expansion? You're interested in 3 dimensions, if I understood you correctly.
Mm-hmm.
And there's a complementary to the epsilon expansion. It's closely related, but it's somewhat complementary. Has somebody looked at that in the fixed dimension expansion?
Yeah, I think these authors here, Calabrese, Paruzzini, and some of their collaborators have looked at it in the fixed dimension expansion. Yeah. And Pellisetto, Vicari have done work on the fixed dimension expansion, a lot of work, and I think they have looked at this there.
And it agrees with the epsilon expansion?
Well, it does have, I mentioned it here, it does have this, let me go to the, this is what I wanted to say here in this Pellisetto and Vicari citation. In the fixed dimension expansion that they do, they fix epsilon to 1, then they resum the beta function, and then they look for fixed points. And they have found hints for a distinct universality class, not the one of the epsilon expansion.
I mean, the fixed dimension is, I mean, what?
Sorry, I couldn't hear.
Sorry, the battery is dying on that one. The fixed dimension expansion is useful for a crossover. You expect to be able to capture the crossover between those two, so between those 2 fixed points. So that might be an additional reason to look at it. But okay.
Okay, more questions?
Excuse me, I ask a question.
Yeah, please go ahead.
I'm Takehiro Azuma from Setsuno University, and I want to ask whether the behavior of king is related to the order of the Fair transitions here. I think you showed several plots of.
Yeah, so good. Here, let's use this as an example.
Yes.
We see a very sharp king when n is large enough. And we want to say that this corresponds to the theory U2 times U20 symmetry that we found with the large n results, since there is such good coincidence of the position of those analytical results on this plot with the kink. At some point, as I was explaining back here, there is a critical value of n for which we transition to situation 2, where we lose the fixed point and we have a first order transition at that point. And here you see a reflection of that in the fact that this kink becomes milder and eventually goes away. There is no known at this point criterion for precisely determining this value, this critical value of n, based on the smoothness of the king or something. This is a work in progress to understand how to, I mean, many people are looking for such a way in the Bootstrap to understand how to find the transition from second order to first order transitions. It's not something we can say conclusively. And we don't even know that if a kink exists, that it isn't because of some very weakly first order transition.
Thank you.
So this is a good question, and it's many people in the Bootstrap community are thinking about this problem.
All right.
Okay, I see that David Schaich has a question. Please fire away.
Possibly a silly question if the mic holds up on me. I'm wondering if you can say anything more generally about the importance of these U1 factors. So you spent a lot of time at the start motivating the effective restoration of this U1 axial to motivate looking at these UN. Battery?
Sorry, I couldn't hear.
So I'll switch to a different mic. This one is on. So say the question again. Is it feasible for you to repeat this analysis with SUN groups, and from that be able to say anything about how much the U1 matters more generally?
Yes, very good. That would be the next step we are considering now. Absolutely, yes. it is something, the bootstrap is something we can use for any global symmetry. And SUNF is more complicated than UNF in some sense, because, it has more, the group theory is a little more complicated due to the presence of extra invariant tensor, antisymmetric stuff. And we want to work it out. We have not yet, but it's definitely something we can do and we're planning to do.
Thanks.
Okay, so let's thank Andy again.
Thank you.
Next speaker is Judah. Judah, are you there?
Hello, can you hear me?
Hello.
Do I sound all right?
Yeah, very faint voice. Maybe you can bring the microphone closer to you. Hello?
Is that any better?
No, we cannot hear you.
How about now? If I sit closer?
Yeah, this is better. Yeah.
Okay.
So maybe you could start sharing the slides.
You see the slides?
Yeah, yes. Are you ready?
Yeah.
Okay, so our next speaker is Judah Unmutioke from Fermilab. So Judah is going to talk about Ising spin and gauge on hyperbolic lattices. Judah, over to you.
Thank you. Thank you for inviting me. I'm going to talk about the Ising spin and gauge models, so simulating these with Monte Carlo methods. Hyperbolic lattices in 2 and 3 dimensions. And so this is work done with my collaborators at Syracuse, Assad, Simon and Jay, and Royce. And so I'm going to primarily just be presenting results. First, I'm going to talk about gauge because this is the work in progress and it's maybe the one that's more exciting to me, but it's also quite incomplete. But at least it's more fun to talk about. And then if, I can move on to the more boring one later on, but there's a paper on this one. So if I don't get through everything and I'm crunched for time, I can just burn through these. But this one I'd like to talk about. Okay, so let's talk about C2 gauge here. I'll just sketch out the model here for you. Hopefully it's somewhat familiar. So this is gauge theory with little Z2 fields, and they live on the links of this lattice. Well, this lattice is a 4-3-5 lattice, and I'll show pictures of what this is so you can get a better idea. But this is a hyperbolic lattice. It's basically made up of cubes, but instead of four cubes around an edge, there's 5 cubes around each edge. And this gives it this negative curvature. So the partition function for this model is here. You've got the Ising spins, and they live on the links around the plaquettes. So it's a square lattice, it's a cubic lattice still. And then you've got a coupling here that I denoted beta. And so this is a pretty straightforward normal partition function for Z2 gauge theory. That's the right point. So this is what the lattice looks like. So it's a cubic lattice, as I said, and so the spins are on these links, and they interact around a plaquette. And so here I've shown several layers of how this is built. So there's like, for instance, you could start with a central cube, and then you could put a cube around each one of those. And then you could put a cube around each one of those, and so on and so forth. And you can just, you can if you try to follow, some cubes here, so these two are sandwiched inside here, and you'll notice there's 1, 2, 3, 4, 5 cubes around this edge, and this is just built up recursively in this way, and this is what makes it hyperbolic. But other than your normal, flat space cubic Ising model, Ising gauge, it's the same model. We're just simulating it on this different lattice. Okay, here are some minor simulation details, just for the people for the numerical scientists who like to see this stuff. It's convenient to rewrite the action so that you basically have the spin you're interested in, and then the surrounding staples of the plaquettes that share that. And we did the simulation using the heat bath algorithm. And for the analysis of the data, we binned the time series data to assess autocorrelations, and then after doing the binning, for error estimation, we use a single elimination jackknife. And then whenever I show fits of the data, they're correlated. Okay, so now I'm just going to start getting into some of the results, and I guess you guys can talk to me about them if you want. But otherwise, I'm just going to present where we're at in this study and how we understand it, if at all. So here I'm plotting the average plaquette and the plaquette susceptibility only on the boundary. So, the simulation, let me just, it's later. The simulation, all these, the spins live on all these links, and, the simulation runs with all these links. But what I'm computing is just the average plaquette on the boundary plaquettes. And similarly, just the susceptibility on the boundary. And so you can see here, it's a pretty seemingly boring average plaquette. It seems to rise pretty linearly just from 0 and then plateaus at around 1 where it should. And the susceptibility, also nothing remarkable. I mean, not unexpectedly, just because of the way this curve looks, but you can see it's also not particularly interesting. And there's very little volume dependence. So I'm just showing one volume here at a reasonably large lattice. And there's basically no volume dependence in these two observables. Okay, so we don't have to look at these quote unquote, this thermodynamic bulk quantities, even though that was on the boundary. We can look at something else. So here is the Wilson loop. And so the Wilson loop is this closed curve of fields. So in the Z2 gauge, it's simply the product of the Z2 fields around a closed loop. And so here you can imagine on this lattice, what you do is, you construct some loop on the boundary. And then there's a corresponding minimal surface through the bulk and the corresponding surface on the boundary itself. And that relationship between this sort of interior minimal surface and the boundary surface, we can use to understand some of the expected behavior. So here's another picture of, an example of a Wilson loop. And so using the strong coupling expansion, you can find that basically for each plaquette, the leading order term will be a minimal surface that connects this boundary loop through the bulk. And it will go through the bulk because that is the least number of plaquettes you can get involved by diving inside. And each time you activate one of these plaquettes on the inside, you get a factor of tanh. And so you can see just running through the bulk, the Wilson loop is going to be exponential, where exponential in the area, in the surface area in the bulk. But we can, just to get an idea, we can use this continuum relation. So you would expect in the ideal situation that the amount of area on the boundary here is exponentially larger than the amount of area in the bulk. And so that's what I've got here. I've got some factors of the curvature for dimensions, but basically the important thing is that you can see that the amount of area in the bulk is logarithmic in the amount of area on the boundary. And so if you use this relation just to get an idea of what's happening, so I'm just going to put it right up here. You can see through some simple manipulations that looking at the boundary area, that the Wilson loop is expected to have some sort of power law behavior. So I can show you what we've got so far. It's not exactly power law. So here's a few examples for a couple couplings. And what I found is that the actual best fits still have an exponential component. So I fit with a form that's got a boundary area exponent and a power law in the boundary area. And so another way to think about this is that not only is there this kind of continuum expected relationship, but then there's a piece that's proportional between these two. At least, you know, I've tried several fits, but this is the one that I feel is the best right now. And so, but other than that, it's a good fit. I can tell you that, you know, the p-values are completely reasonable. And so this is you know, almost certainly an artifact of discretization, and probably, as we've been discussing, there's probably some discretization effects that I'd like to understand about the perimeter and the kinkiness. And that's maybe I'm just, you know, wrapping this up here in some effective way, but I need to spend some time thinking about it. But ideally, it would be nice to isolate just this power law contribution as I work through this. Here's some other plots of it, though. So this is the Wilson loop. So I've made a 12 by 12 loop on the boundary, and here now is a function of the coupling. And so you can see there is some sharp transition from essentially 0 to non-zero, but this is getting this location to settle down is difficult. So I'm not sure how unique this point actually is. So I'm still looking into this, trying to see if there's actually anything interesting going on here. And then here's the Wilson loop for several values of beta now as a function of area. So this is like the previous, but I just want to show you the coupling dependence. So as beta gets larger and larger, you can see this thing really softens. It stops to fall. It stops falling so dramatically. But even for, you know, you get to really small betas and this thing is just dropping extremely quickly. Okay, so this is another observable we can look at, is this plaquette-plaquette correlator. And so this can tell us about the glue ball mass. And so again, you can imagine you have two boundary plaquettes, and you can think of how they're talking to each other. Well, the easiest way for them to talk to each other is to create a minimal tube through the bulk, and that's what requires the least number of plaquette excitations to make a valid configuration. And so you can see maybe with your eyes that there's only a handful of cubes that actually are involved in this tunneling process, or this tube here, but you can see on the surface there's tons and tons of plaquettes on the boundary. And so again, basically for each plaquette in the tube, you get a factor of tanh, and you can see that it's clearly exponential through the bulk. So this is the bulk distance. But then again, trying to use this continuum relation to see the leading order or the expected behavior by substitution, ideally there would be again some power law in the boundary distance between these two plaquettes. So here's some data. This is much more noisy, unfortunately, and it's dominated by very early distances. And so again, it seems that this exponential with the power law part seems to do the best job of fitting, although, you know, it's pretty competitive between just this, and both together, as you can imagine. You know, the thing falls off extremely quickly. So again, I'm still trying to extract a signal here, a power loss signal, but that's still a work in progress. So, but I still want to show you some of the data about how this correlator is looking for a couple couplings here. Okay, and then if you take the power from the previous fits seriously, and you think, you know, that's it, then you can plot them as a function of the coupling and see what that looks like. And so the fits, you know, because of the extreme fall off, the speed that this thing falls off, you know, basically all the results over here are very hard to appreciate. But in this intermediate range, you get pretty reasonable fits, and the power stabilizes. It's almost roughly constant for some range. And then again, as it really starts to, as the correlator gets flatter and flatter, the fits are a little rough again. But maybe, you know, if you can take this seriously, maybe there is some sort of constant power law behavior for a range of couplings. Okay, so at least on the 3D gauge part, there's a possibility for this zero string tension up to these discretization effects that I believe are, you know, causing this exponential behavior in the actual Wilson loop and the correlators as well. So there's evidence that you could maybe extract a massless glue ball on the boundary, but I got to figure out how to deal with these discretization effects that are still causing these this exponential dependence. On the quote unquote bulk quantities on the boundary, there's basically, you know, when I compute these, whatever you want to call them, thermodynamics or thermodynamic quantities or whatever, there's very little volume dependence. But they seem to converge pretty rapidly. Okay, so anyone have anything they want to say before I start talking about the spin model?
Judah, hi.
Hi.
How are you doing?
I'm well. How are you?
Good. In the plaquette correlation function, shouldn't you have a disconnected diagram? There's no quantum number that distinguishes it from the vacuum.
I think I understand what you're saying, but you're just saying there should be, you can have little cubes out here.
No, I'm saying that when you have a correlation, but you have a correlation between two plaquettes, as you pull them apart, you should have a constant term. That's the disconnected diagram. In fact, if I look at your curves, I see a constant term. I see the disconnected diagram.
I do subtract off the vacuum part.
Oh, you subtract off the vacuum.
I subtract off this squared, yeah.
Oh, okay, good. Then you've gotten rid of that. Okay. All right, that's fine. So, all right, so now you're trying to find the excited state, but that makes it very noisy because you do that subtraction, right?
Yeah, I mean, yes, it's extremely noisy.
Yeah, okay, good. Anyway, now I understand. I was wondering where they did that. Okay, well.
Yeah, this is just the connected piece. I didn't mention it, I'm sorry.
Okay, fine, that's good. I mean, this is sort of obvious thing to say. You have only a few layers and you've got I think a pretty violent negative curvature on the edges, right?
Yeah.
So I would think that, you know, it's a pretty crude approximation to a smooth curvature.
Yeah.
Which is another way of saying discretization errors are pretty dramatic. I mean, to be honest, I'm surprised you get as much as you do. So that's very nice. Thanks.
Yeah, thank you.
You can see how that's, because I mean, you have 5 cubes around a point. That's kind of a pretty violent negative curvature, right?
Absolutely.
Okay.
Yeah, I mean, I think it's the first few steps in both of these are dangerous.
Yeah,
and
yeah.
it's also where almost all the curvature is coming into the fit. So I have to spend some time still working on this.
Anyway, it looks amazingly good, as a matter of fact. It's always surprising. So anyway, thanks a lot.
Thank you.
Right. So could I ask quickly, do you hear me?
I do hear you.
Yeah, so did you try for other lattices? How much do this alpha 0 and alpha 1 depend on the choice of the lattice, in case you tried that?
I have not. I mean, in the 2-dimensional study that I'm going to talk about soon, we tried several lattices, but in this 3D one, I've only worked on this cubic lattice.
Okay. And in this case, sorry.
It's a natural and a good idea, what you suggest, and I just need to find the time to do it.
Okay, maybe wait for the second part. Thanks.
So now this is published work. So like I said, when the organizers let me know there's 5 minutes or whatever, I might have to burn through some of this, but you can find all these results in our paper. Okay, so this now is in 2 dimensions. And so this is the spin model. So the fields are located on the vertices of this 3-7 lattice. And these are triangles, and there's 7 of them around each vertex, as opposed to 6, which would be a normal flat situation. And again, it's a very vanilla partition function. It's the IISER model. So you have this nearest neighbor interaction between these Z2 fields. There's a coupling, usually thought of as 1 over this statistical temperature. And then it's a nearest neighbor interaction. So let me show these results these are just calculations of boundary observables. Now, we do the simulation over the entire lattice. So the spins sit everywhere, even in the bulk and on the boundary. And just for the sake of intuition, I present here kind of a pedagogical walkthrough using the high temperature expansion to visualize some of the, you can visualize the correlation functions and the correlations between the boundary spins may be easier. So when you do this high temperature expansion for the IISER model, you basically get an expansion over closed intersecting loops that are weighted by this factor of tanh beta. So for each bond or each link involved in your loops, you get this factor of tanh, and then you sum over all possible diagrams that you can construct where these are closed. So here's just an example of these little bubbles. And this is the 3-7 lattice in the Poincare disk. And for the spin-spin correlator, you can still do this high temperature expansion. And what you get instead when you place a source and a sink spin is you get connected paths between the source and sink with little disconnected pieces that we were just talking about that kind of float around out, little bubbles that float around out in space. And then this connected path between your source and sink spins for the correlation function. And so now you can imagine you have 2 boundary spins, and you want to look at the 2-point correlation function between them. And like before, basically for each, it's clearly shorter to pass through the bulk. So, you count the number of edges here involved between connecting these two spins, and there's 10 or something. And then on the boundary, it's outlandish. And so it's a much better, it's a much safer route to travel through the bulk. And you can see then that contribution would be exponential. So the leading order behavior for this correlation function is exponential through the bulk. And we can do the same thing as we did before. Did anything change? Can you guys still see the presentation?
Yes, we can see.
Okay, my computer just told me something odd. Okay, fine. So now again, you can there's an expected exponential relationship between the number of edges, the distance here through the bulk, and the distance along the boundary. And so this bulk distance is logarithmically related to the boundary distance, like this. And then using this in the bulk correlation function, you can get an idea of this leading order behavior on the boundary, which is power law, where this is the power. It involves the coupling, the radius of curvature, and some prefactor. So you would expect roughly this behavior. And so let's try to fit this and see what we get. And so now here, so there's a few temperatures here. And this is in a different set of variables. It's not actually in terms of the boundary distance per se, but it's just the angular distance around the boundary. It's okay. It doesn't matter much. I mean, it matters, but it's roughly the distance. So this is the correlation function, and we fit to an ansatz. So now we do have the disconnected part included in the fit. So we have an overall constant.
You have 5 more minutes.
Thank you. So we have an overall constant shift, and then a prefactor, this angular distance around the boundary, and then the power law. And we find pretty good agreements. You can see the chi-squareds are pretty reasonable, and the p-values are pretty good. And so for a range of betas, it appears that the 2-point function from between boundary spins is consistent with the power law. We can also look at the boundary observables. So this would just be computed with the spins, the bulk observables, quote unquote, computed with the boundary spins only. And so we can look at like the absolute magnetization or the energy, and then the fluctuations of these two quantities. And these are just, in how you'd expect them to be. So the sum over the spins. This one, I mean, this is a sort of a misnomer, but it's actually, it's this interaction. It's the nearest neighbor product between spins. Calling it the energy might not be the right thing to say, but it's this observable. So the product of nearest neighbor spins along the boundary, and then the fluctuations in the magnetization in this quantity. And so here is the magnetization as a function of the temperature. And here's the magnetic susceptibility as a function of the temperature. And these are the number of sites. So this is the size of the boundary as the lattice grows larger and larger. And so we can see that at least for this range of volumes, the magnetization, it might be sharpening, but it's not sharpening particularly quickly. And at least at these volumes, it does not appear to be changing spontaneously. The susceptibility also does appear to be growing, but it's growing very small, and it's not very large. But it's incrementing consistently each time. It's also very symmetric. So if you look at maybe the largest two volumes, it's not getting sharper. So it doesn't seem to be narrowing much either. It seems to be a whole wide range that's actually growing consistently larger and larger. And so we suspect there's something going on here, but we don't have anything conclusive. But we can look at, for instance, the scaling of the susceptibility as a function. So, we can look for power law behavior in the scaling of the peak of the susceptibility. And so here, for one temperature, so this is, so this is not the peak. This is for a few temperatures. And so this is the log of the number of boundaries. So this is like log of the volume versus log of the susceptibility at that temperature value. And we find a reasonable fit for power law divergence, where this is the power. At a little hotter temperature, it's also a fairly sensible fit quality, also diverging. And this is kind of at the peak. I think 3 is basically at the top here. And then even higher temperature, to the eye, it's seemingly a good fit, but to the computer, it's not great. But there's roughly power law growth here on either side. And these are somewhat symmetric values about the peak value. And moreover, you can relate the divergence of this susceptibility, so the exponent that the susceptibility is diverging, to the 2-point correlation function. So this susceptibility is the integral of the 2-point correlation function. And so by noticing that, if you put in the expected behavior, so this power law behavior for the 2-point correlation function, and you do the integration, the scaling of the susceptibility, so the exponent of the scaling is related to this delta, which was the power involved in the 2-point correlation function. And so that's here. So the susceptibility divergence and the power law are seemingly related this way, at least approximately. And when we compare them, so if we, using that relation, if we take the actual power law that we calculate from fitting the correlation function, and we take the exponent from the diverging susceptibility and rescale it to make it equal to, supposedly equal to this delta, we find pretty good agreement between the power law and the susceptibility. So this is nice evidence that at least the fits are consistent with the susceptibility on the boundary as well. So then, yeah, I'm gonna skip everything and I'll just show my conclusions. So some dual lattice stuff here, which is interesting. But so yeah, for the spins, for the Ising spin system, we find 2-point correlation functions that are consistent with power law behavior. And these power law correlations would support the idea of conformal field theory living on the boundary. And ultimately, it seems that this power law behavior is really related to this exponential growth in the amount of space on the boundary as you move out from the bulk. And it appears there's perhaps some sort of phase transition on the boundary, but we're not sure what universality class it lies in, and it needs to be analyzed a bit more. Thank you for your attention.
Thanks, Judah. Time for questions? Yeah, Rich.
This relationship that you have between delta and gamma nu, that should only be there at a critical point, right? So the fact that it occurs off of the peak indicates to me maybe it's just mean field theory or something. There's really no critical point, right? Isn't
yeah,
that
I mean,
right?
Maybe our argument was not that. Instead, we thought that there might be a line of critical points.
Well, that's what I'm saying. It looks like it's critical everywhere, because isn't that right? That relationship you wrote down between delta and gamma and nu is a critical relation of scaling, right?
Yeah, I mean, wherever this.
Right.
Holds,
so the fact that
yes.
you see it fitting over a whole range suggests that you have a line of critical points, not a critical point.
Yes,
right.
I agree.
Okay. Okay, good.
Yes.
Okay, more questions? Seems like there are no more questions, so let's thank Judah again.
Sorry.
Okay.
Anosh, may I?
Yeah,
do you have
please,
time?
please,
Do you have time?
please
Yeah.
go ahead. Yeah, please go ahead.
What is the dependence on the number of boundary points in this 2D and 3D case? We didn't have time to talk about it, I suppose. And the dependence on the lattice that you mentioned.
Oh yeah, the dependence on the lattice. Oh man. So when we calculate here, so I don't have the table on me, but okay, so we can try to extract the radii of curvature from, okay, I have to recalibrate here. So we've done fits.
In the 3-7 lattice, it's a fraction of the total number of points. I think it's a golden ratio.
That's right.
You know, it's a fixed number. Maybe I say we have also done these lattices, but in a different geometry. It would be interesting. We have the 3-dimensional lattice in the cylinder geometry, and I think this is a question. I think that we should get the same results as a coordinate transformation of your results.
That sounds totally reasonable. Yeah.
So I mean, now you're way ahead of us because we not managed to get there. So who knows? Maybe you can come help us get there.
So by cylindrical geometry, do you mean that the cross sections are hyperbolic and you have regular Euclidean in the z direction?
Yeah, we have a lattice in which we have a cylinder, which is another possible. We have a lattice which is it's got this hyperbolic disk. So we actually have the triangulated one that you showed first. So we have a plane. Yeah, we have this kind of triangulated lattice across slices, and then it's a cylinder going down. It's not a direct. Yeah. It's the global ADS, if you like. And
I understood.
And so but that's supposed to be a coordinate transformation to go from the ball to the cylinder, and therefore you would think that we could do a coordinate transformation on our correlation functions and get the same thing. That's of course not obvious that it'll work in this discrete form, but it does give two ways to look at the same problem. But I say we haven't gotten anywhere near this kind of simulation. I need another student or another person. Anyone who want to volunteer? We got the codes written. We can hand them to you.
Okay, maybe one more question, one last question. I don't see any. So let's thank Judah. So with that, we are coming to the concluding part of the program. So David Schaich will give the concluding remarks.
That I will, yeah. Anosh asked me to give some concluding remarks, and I'll try to keep these relatively brief and just maybe start off by saying the personal reflection or impression. I always like coming to these sorts of meetings as someone firmly rooted in lattice field theory. This is really the best opportunity there is for me to get beyond that domain and encounter things like stringy holography and all of the gravitational side of the work that I'm connected in and involved with that I wouldn't otherwise encounter. So I hope that all the rest of you are feeling similarly. Those of you based on the gravitational side have enjoyed learning a bit about lattice field theory and lattice supersymmetry, and all the other lectures we have. So I want to, on the basis of that general reflection, want to thank all of the speakers we've had, the lecturers, the research talks, both those who have been able to come here in person as well as those who have had to join us online, even though it's disappointing not to be able to chat with the online speakers in the tea breaks and the dinners and the evenings. It is also, I think, a positive outcome of what we've had to go through over the past 2 years, that we've developed this capability for people to participate even when they haven't been able to make it here to India in person. And also acknowledge that many of those who are participating are doing so at somewhat awkward times, very early in the morning or late at night. I think for Judah right now, it's rather early, and for Anne at the start, she was giving us lectures on lattice field theory around midnight in Colorado. I also want to thank all of you in the audience, even those who weren't presenting, again, both in person and on Zoom. We've had lots of great questions coming in on all the presentations, which has helped to make this program more dynamic, more insightful, and more informative to all of us. And that takes me to really thanking the people who have made this all possible, maybe starting with Anosh as the driving force behind the organization, and extending from Anosh to, okay, well, okay, Anosh and then everyone else, but specifically giving acknowledgements to all the staff here at ICTS who have helped to make everything run smoothly, from the cafeteria to the guest house, all of the audiovisual techs who have got everything set up, streaming, remotely connected, and running, and keeping the microphones in good supply, and especially mentioning Gayatri in the program office, who I suspect all of us have had a lot of communication with to get the logistics in place. So let's thank those folks. And as a final closing remark on the closing remarks, I was reminded attending this program that this is actually the second time we've had these numerical holography workshops here at ICTS in Bangalore, but it's actually the 6th in the overall series that goes back to 2009 in Imperial College London, followed by workshops in Santa Barbara, in Kyoto, and in Edinburgh, as well as the first round in Bangalore. And I suspect this will not be the final entry in this series of workshops. So I invite you to think about where and when you might next like to have this sort of encounter between the string theory, holography, and lattice field theory, numerical, conformal bootstrap, all of these communities getting together. You are, of course, all warmly invited to the Lattice 2024 conference in Liverpool in 2 years. And we can think about whether to have future installments of this workshop series there or somewhere else in the years to come. So thanks again for coming and sticking with me to the end of the closing remarks. And thanks again to everyone who's helped to make this possible.
And also thanks to Dave, who also did a lot of work and didn't thank himself.